Dennis Madden here with Gears Overdrive. Gears Overdrive is a supplement to the articles in Gears magazine. Some time ago I did an article on converter pressure and specifically targeted at crankshaft failure. I've done a few of these over the years, and every now and again, every couple of years, this subject comes up, and there's a number of reasons that are cited for crankshaft failure, all related to the torque converter, most of which are false. So I wanted to take a moment and clarify a few details on how the converter generates pressure against the crankshaft and what are the causes of crankshaft bearing failure. Now, to do this, I used a jig. I set this up some time ago. So you'll see the pump on the bottom sitting on a scale, torque converter, and then a flex plate. The rod of the press is focused right on the pilot. We'll talk about the flex plate a little bit later, but this is going to set up the entire situation so you fully understand what's going on with converter pressure and crankshaft failure. Now, one thing to get up to speed on is how do we figure out the math behind crankshaft force, the thrust exerted on it. And it's simply this. It is the area of the converter hub. In this case, it's a 2-inch hub. Divide it by 2, that gives us a 1-inch radius, multiplied by pi, which is 3.142, rounded off, which gives it about a 3-inch, a little more than 3-inch area. And it is that area that is working on the crankshaft bearing. Consider it no different than a servo piston or a ram. If you've seen a ram on a tractor, for example, you'll see that shiny rod that oil works against. So it's the pressure inside the converter multiplied by the area of the hub. That is what is at work. Now, you'll typically see crankshaft failure more common in General Motors vehicles, specifically those that are in front of a 400 transmission, a turbo hydromatic 400. And the scenario works something like this. Someone has a motorhome, that's very common, has a motorhome, and they decide to get the engine rebuilt. So they get the engine rebuilt, and while it's all disabled, you might as well get the transmission rebuilt as well. From that point forward, it cannot keep crankshaft thrust bearings. It just wears them out right and left. And there's all sorts of ideas about converter ballooning, etc., that are the cause of this, which is not true. So let's take a look at this example. Now, be aware that this jig, the converter and the flex plate, weigh about 30 pounds. If we take our 3-inch hub, it's going to take about 10 psi just to equalize that weight. And so this is really, in effect, where it says 40 psi on the gauge, in effect it's working as though it's only 30, and or maybe even less. Which is why the numbers don't quite add up on this. They're pretty close. So what happens is that 40 pounds of pressure that you see, it's overcome the weight of the converter, and now it's pressing on what would be the crankshaft, but now it's pressing against this rod of the press, and you can see we have 82.8 pounds of force. That would be the equivalent to crankshaft pressure, or the force against the crankshaft thrust bearing if this were in a car. Now, the difference being that it's sideways instead of vertical, so it doesn't have to overcome the weight of the converter moving forward. But I still want you to understand the condition at work here that actually produces that force. And obviously you can see that there's nothing working inside the converter. There is no engine attached to it. There is no transmission. This is purely the pressure inside the converter multiplied by the area of the hub. If we raise pressure some, notice that we're at 50 psi, again overcoming the weight of the converter. This is behaving more like there's 40 psi in it, because like I said, it takes 10 to overcome that weight. We're almost at 120 pounds of force. And as you continue to go higher in pressure, internal converter pressure, that force exerted on the crankshaft will increase. And it can increase so great that it damages the thrust bearing. Now, what are some of the things that will inhibit this pressure getting too excessive? One is cooler flow. The pressure inside the converter can escape or will escape into the cooler, and that's one of the things at work that keeps the pressure down. This is fully contained in the jig that we're using, but if it were in an actual car, that oil would be going out to the cooler, returning through the lube circuit, and that would help to reduce the pressure inside the converter and reduce the force on the crankshaft. Some transmissions will have a converter regulator where they'll limit the pressure inside the converter to 25 pounds or some number that the engineers have decided works good for their application. But it's important to understand this concept. Now let's talk about converter ballooning. And we'll see every now and again where someone will cite that the converter ballooned and exerted force on the crankshaft. Now stop for a moment and let's just think this through. If the converter is ballooning, and that's from excessive pressure inside the converter, and it were going to push on the crankshaft, it would also have to push on something in the transmission. That's the fatal flaw with this concept. And what it's going to push against is the pump gear, the inner pump gear or pump rotor, and it would wipe out the pump very quickly. But here's the missing element to this component in this thought. If pressure is high enough to balloon the converter, you surely have internal pressure that is going to push on the engine through this calculation, which is simply the area of the hub multiplied by the pressure. So it's a false claim that it's the converter ballooning that did the work or did the damage, but rather the high pressure causing the converter ballooning also caused the excessive force through the simple math of pressure times the area. It did not thrust against the inner pump gear or do any of this other work that are often claimed. So it'll go up in pressure just like you see in this example that we have. Now, what about the flex plate? It's also been cited that the flex plate eliminates some of that pressure and is actually absorbing the force exerted by the converter. That's also not true. The flex plate serves an entirely different purpose, which I won't get into right now, but I've set up the jig to demonstrate how this works. Notice that there's a hollow hub sitting over the pilot and resting on the flex plate. So this would be where the crankshaft is actually bolted to the plate. So the force going through this jig is the mounting studs through the flex plate onto the mount where the crankshaft resides. And we can go through the very same measurements that we had before, 40 pounds, which offered about the same 80 psi. And if we were to raise that further, it would give us about the same amount of force that we did in our earlier example. The flex plate does not eliminate the force on the crankshaft. It serves another purpose. So when you're looking at this condition It's a matter of the area of the hub multiplied by the pressure inside the converter. That is the vast majority of crankshaft problems if it's related to the transmission. Now, I've gotten a little deep in this, and I wanted to make sure not lose sight of something else. We also see this condition where someone rebuilds the engine and all of a sudden can't keep thrust bearings alive. And this is in front of a transmission that didn't have problems. The vast majority of the problems that we've found with crankshaft failure or thrust bearing failure has to do with the method of machining the crankshaft. Now you say, okay, well, wait a second. That doesn't make any sense because it's more prevalent in General Motors engines in front of a turbo hydromatic 400, but less prevalent in Fords and Chryslers. Why might that be? The main reason is that transmission does not have any regulating system whatsoever to limit the pressure inside the torque converter. It is strictly due to the amount of oil flowing into the converter and what can escape through the cooler system. So one thing that will confound this is adding a cooler. And when you add a cooler, you've just increased, particularly if it's in series, you've just increased the amount of pressure inside the torque converter, which will exacerbate this problem. Another thing along these lines is that many transmissions that have a converter regulating system operate at a much lower pressure. So the methods of machining that may be inferior for a General Motors transmission that is going to operate at a higher converter force against the crankshaft will work in a Ford or a Chrysler or any transmission that has a regulator system and keeps that pressure down. Adding a cooler will have very little effect on an engine that or a transmission that has a regulating system because it will internally keep that pressure lower. That's why we see that mostly on General Motors and mostly the turbo hydromatic 400. Now there is another failure that we see that is not as common, but I wanted to bring it to your attention, and that is under normal operation of the converter, there is a pressure head that develops on the front side of the converter. And it's going to push the turbine and the converter housing, the front part of the converter housing, away from one another until all the clearance is taken up. And then it's simply an internal force that, on the bearing. It doesn't create any more pressure on the crankshaft and only uses what we just talked about, that is the area of the hub and the pressure inside of the converter. But you can have an effect that can be pretty damaging. One is an excessive amount of clearance in the converter. And two, because of a high performance atmosphere that it works under, the pressure head is rather high. And we'll see evidence of this when you look at a converter where they've contacted one another, where the turbine and the main housing of the converter have contacted each other. Here, you'll see it, these bent fins, a little close up here. All right, that's due to an excessive amount of internal pressure at that pressure head point, plus additional clearance where those two components can meet one another. And the other thing that that is required in this is a spline lock condition, which is common. You'll see that in just about every application. What does that mean? That means because of the torque on the turbine, the spline doesn't want to flow or ride smoothly between the converter turbine and the input shaft. So now, when that head exists and there's excessive clearance, it's going to put an extreme amount of load toward the crankshaft. And it's going to continue that. It's almost like putting the thrust bearing in a vise. It's going to continue that until the clearance is used up inside the converter. Now, this is not the common method of crankshaft failure by a long shot, but it does exist. So, what can you do to eliminate it? Make sure that your crankshaft is machined properly. Make certain that you have a low or a lower amount of cooler flow pressure. Avoid adding a cooler if at all possible. 25-30 psi of converter pressure is just fine if you're able to lower that. I know there are kits out that will bypass portions of the cooler to lower that pressure. Also, you can add a cooler in parallel where the two lines break off and go into two separate coolers. That will actually lower the amount of internal converter pressure. But the key in most all the cases that we've seen is a flawed method of machining the crankshaft thrust surface. But now you know that this is normal for the converter to press on the crankshaft. We know that the flex plate doesn't do anything to absorb that. It's simply a math problem. Converter hub area times internal converter pressure. Thank you very much.